All right, time for the 2025 AP Physics 1 questions. Just like in the Physics C videos, we're just going to go ahead and kind of jump right into it. And yeah, we should be able to probably finish the whole thing in one sitting, just like with the Physics C videos as well, too. All right, let's go ahead and just jump right into it. So question one, mathematical representations. You've got two things. One has a mass 5 times greater than the other. Oh, okay. Wow. Okay, this should not be too bad then. Okay, sketch a graph for the momentum of the block cart system. Uh, it is going to just be total momentum is conserved, so that's pretty easy. It's just going to be a straight line. Oh, that's not even close to straight. It's just a straight line the entire time. There's no external forces, and therefore, you're just going to have total momentum as being conserved. Um, yeah, pretty easy for part one. Okay, derive an expression for the final velocity of both of them. And okay, so then they both continue to move to the right at a constant speed. So for A part two, this is just going to be conservation of total momentum to find the final velocity. So we say that initial momentum is equal to final momentum. So MC VC is equal to MC plus a fifth MC times VF. So that's going to give you VF is equal to, assuming that I'm doing my math correctly, 5/6 VC. There you go. So A part two is just going to be conservation of total momentum. It's probably only worth 2 points, one for writing conservation of momentum and one for solving for it, maybe 3 points. So the graph is probably just worth a point or no, 2 points, I would say, for the graph in A part one, showing that total momentum is conserved and that it's constant as well. A part three, derive an expression for the change in kinetic energy. That's not too bad. I'm just going to do it up top here. Change in kinetic energy is equal to final kinetic minus initial kinetic, which is 1/2 times your final mass multiplied by final velocity squared minus 1/2 initial mass times initial velocity squared. So that should give us, let's see, you're going to end up with 3/5 mc times 25 over 36 vc squared minus a half mc vc squared. All right, we got to cancel a lot of stuff here. So 5 over 12 minus a half. Oh yeah, no, it should be negative. You should have a negative change in kinetic energy. Wow. I can't believe I was yeah, negative a 12th mc vc squared is your change in kinetic energy. So I'm just taking initial and final, right? Taking my expression from velocity from A part 2, plugging that in for final velocity and simplifying it down. All right. Consider a case where the new block is dropped and collides with the top of the cart, but now it slides along the cart, which means that there is going to be some friction. Um, the time that it collides and moves together and there is frictional force, determine whether the momentum of the new block cart system increases, decreases, or remains constant. Well, both the block and the cart are still experiencing equal opposite forces according to Newton's third law. It still has to be constant. Yeah. So both carts, unless I'm just really underthinking this, I think it has to be constant because both carts experience the same friction force, uh, for the same amount of time. But in opposite directions because of Newton's third law. So therefore, they experience equal and opposite changes in momenta or impulse, which is equal to change in momentum. So total momentum is still constant. Yeah, total momentum is still constant. There we go. Yeah, I think that's it. Probably just 2 or 3 points I would guess probably 3 points for part B, one for getting the correct answer, one for talking about same force, and then one for talking about same change in momentum then. So not too bad. All right, let's go ahead and move on to the second one. And let's see. I have to be careful here because I feel like these questions are I'm kind of underthinking them a little bit, but I'm gonna try my best to not do that. So, okay, a block is released from rest and it slides down with negligible friction. At 8D, it makes contact with the spring, and then the spring is compressed at 12D. Oh my goodness, a lot going on here. Okay, so figure A shows what does figure A show? Let's see. It shows everything at 10D. And we have to draw everything at 60, which is before the spring is compressed, and at 0, so when the block is released from rest. Okay, let's start when it's at rest. That one's easy because all you have is gravitational potential. So that's 2, 3, and 7. So that should give you a total energy of 12 then. No kinetic at the start, no spring potential at the start, and then 12 E0 for potential energy because total energy has to be conserved. At x is equal to 60, you still have no spring potential energy, that's the term. To figure out the speed at 60, um, it's not going to be equal to the speed at 10D if I'm recalling correctly. Let's see. So you go down to you go down 10 units between 0 and 10D, which means you should only go down 6 units between, no, not 6. Yeah, you should only go down 6 units between 0 and 60. So you should end with 6E0 of gravitational and 6E0 of kinetic energy. Oh, wow. Okay. They do actually, no, it's 7 and 6 for kinetic energy between these two. Okay, so my thought process here, and my guess is that you're probably going to get like another 2 or 3 points for these graphs. One for representing the zeros, one for representing equal energies at 60, and one for representing 12E0, or just saying that total energy has to be conserved, perhaps. Yeah. These look a little bit different than some of these sample questions I've seen, so I'm just kind of speculating. I don't actually know how they're going to score them this year, but total energy is conserved. Kind of taking the difference in gravitational potential between 0 and 10D as 10E0, you should expect there to be a change of 6E0 between 0 and 60 for the potential energy. Since total energy is conserved, it should always equal 12E0. Okay, I'm confident in that. All right. So figure 5 shows the compression, and you have to derive an expression for the spring constant. Okay, that's not too bad because you start with gravitational potential energy, and you end with, say, just spring potential if you assume 0 height when the spring is completely compressed. So that would imply that you have G initial height is equal to 1/2 K times the spring displacement squared. Well, the spring starts at 8D and it compresses until 12D. So that means that delta X is just going to be 4D. Whereas your initial height, we would be able to say that this distance here is 12D, and this is your angle theta, which means that sine of theta should equal your height over 12D. So therefore, height initial is 12D sine theta. So that would tell us that mg times 12D sine theta is equal to 8 kd squared, because 4 squared is going to be 16 divided by the half then. So that's going to eliminate one of the d. Your 12 is going to turn into a 3 if you divide it by 4, and the 8 will turn into a 2. So that tells you that spring constant should be 3 mg sine theta over 2d then. And that is in terms of everything that is allowed, which is good. Okay. Figure 6 shows a graph of the one of the energy. Let me go ahead and clear that. Spring potential energy, that makes sense because it's a quadratic graph from 8D to 12D. Sketch and label the total mechanical energy from for the block spring Earth system. Like we said, total energy is conserved, and since there's no friction, you should just have a straight line at 12E0 for the entire time then for the block spring Earth system. Now, for gravitational potential energy, we said that you should end with 0, and it should just be a straight line, and it should go to 4E0, just like that. It has to be a straight line because gravitational potential energy is directly proportional to position, and it starts at 4E0 because we said that the total energy starts at 12, and therefore when you reach 8D, you should only have 4E0 worth of potential energy. There we go. Okay. Indicate whether the speed at oh, come on. Whether the speed at 9D is greater than, less than, or equal to the speed at 8D. So I'm going to go back over here. Let's take a look at 9D. So you have 1 E0 worth of energy. It should be equal speed, by the way. I can tell that because based on the graph, you have 1 E0 worth of spring potential energy and 3 E0 of gravitational potential energy. That leaves 8 E0 left over for kinetic energy, which is exactly the same as what you should have at 8D because conservation of total energy. So they should be the same. They should be the same speed because of that reason. Justify how your response is consistent. We just kind of said that, but same total energy is conserved. Total mechanical energy is conserved throughout this process. And when you add all your potential energy at both positions, it adds to 4E0. Therefore, you must have the same kinetic energy and therefore same speed to conserve energy. There you go. Okay. Easy. I'm kind of bored with that. Let's move on. Okay, rotation question, it looks like, for experimental design. Students are investigating balancing systems, and you have a spring scale. That sounds fun. You're probably going to put the block on there, I imagine. It can pivot about the center. The center of the meter stick is attached to a stand. Yeah. And there's a hook. Uh, Okay. And the hook can be attached. Oh, got it. Okay, so the hook can be attached to the meter stick, and it cannot be attached to the spring scale. Got it. Okay. You cannot measure the mass of the block just directly. Okay. And you actually have to determine the mass of the block. Got it. Okay. That's not too bad actually then, because what you would want to do, yeah, okay. So this time I actually am going to write out an experimental procedure. I didn't do that for the physics C ones because I actually feel like those experimental design questions were easier than this one. This one's not too bad though. A spring scale measures force, so all you have to do is place the block through the hole at the 60 centimeter mark. Place it wherever you want to start. It doesn't have to be at the 60 centimeter mark, but your next step then is to pull on the spring scale until the system balances out. After you do that, read the force on the spring scale. Actually, sorry, after you place the block through the hole on the 60 centimeter mark, you have to record the position as 10 centimeters because it's the difference between the stance position and the block. Because torque is directly proportional to position. or distance from the pivot point, not the position of the block, and position of the block. There you go. So we're measuring distance. We are reading the force on the spring scale, and you are also going to record the distance from the pivot or the stand to the scale, which is 50 centimeters. And then you're going to repeat the experiment with the block placed at the other three holes. Okay. There you go. Pretty easy. That repetition is needed to reduce uncertainty. Describe how your data could be collected, or how the data collected to could be used to find mass. So how we would do that then is I'm going to first create a sum of all torques has to equal 0. That would tell you that 0.5, because torque is equal to RF, and then you have the sign of phi, which is irrelevant here. So you have 0.5 meters multiplied with force by force on your spring scale is going to equal the distance away from the stand to the block multiplied by the force that the block is exerting, which is just mg. G is a constant. We are varying F and R, so you can find M by plotting Fs on your vertical axis, plot R on your horizontal axis, and that should yield a straight line with a slope that is equal to mg over 0.5. Therefore, your mass of your block is equal to, let's see, 0.5 slope divided by g. So slope over 20. There you go. Not too bad. All right. Students now have an identical meter stick of mass m, so the meter stick now has mass. Hopefully I didn't miss that in the first part. I'm actually gonna, yeah, go back and double check. Wait, no, the pivot is just through the center of mass of the meter stick, so it didn't matter. Okay, identical meter stick where the axle is fixed to the wall and you suspend it horizontally by a string that is connected to a spring scale of negligible mass. Uh, oh, fun. Okay. Um, okay, the angle that the spring makes is given by this, and you're also given that. Okay, you have, this doesn't look all that fun. So you create a graph with 1 over sine of theta, and you have to determine what m is. We, I assume, know that g is 10 here again. Okay, what do you have to plot on the vertical axis? That's easy. It's just, you could plot whatever you want. I'm just gonna make it easy and plot tension. So, okay. All right, and this time they actually did give us some nice major and minor grid lines according to what I can see from the graph right now. So let's go ahead and actually graph it. They've already taken care of the one of sine theta, so we have to now plot tension force. And I am actually going to do that. Those of you who have taken Physics C have probably taken Physics 1. You've probably already done the linearization, so you probably didn't need me to walk through that process. Those of you who have taken, Physics 1, this is probably your first year really doing linearization. So I'm gonna just go ahead and do that right now. So, yeah, force of tension is gonna be in newtons. You gotta make sure to include your labels. What does tension force actually go up to? It goes up to 21. So I have 1, 2, 3, 4, 5 big grid lines, which means that I am going to scale and go 25, 20, 15, 10, and then 5, just like that. So now I actually have to compute 1 over the sine of those values. I will be back in 2 seconds. I need to grab my calculator. All right, little more than 2 seconds, but time is relative, so let's go ahead and do some computing. So, let's see. All right, my calculator consists of my scientific calculator on my phone, so please bear with me. So the first angle that you have is 80. So sine of 80, and then take 1 over that. Oh, geez, this is going to be a pain on my calculator. Uh, okay, so I'm gonna have to write this down on a separate sheet of paper. Actually, no, I don't. What am I talking about? I can just write it on the table here, which you'll probably have to do. All right, so 1 over sine theta, 1 over sine of 80 is going to give you like 1.02. All right. Oh, this is a pain. Sine of 45 is 0.71 already, I know that. So then you should get 1.41. It should just be root 2. Yeah, root 2. Sine of 36, I do not know what that is off the top of my head, but let's take 1 over what my calculator is giving me, and that gives you 1.7. Okay, sine of 31 is probably pretty close to zero point 0.5. Yeah, it's 0.52. 1 over that is going to give you approximately 2. 1.94, I wasn't all that close. And then sine of 22, take 1 over that, and that is going to give you 2.67. So those are the data points that we are going to plot. I am also going to just rewrite tension over here as 21, 17, 13, 12, and 8. And if we plot all of that, we should get a straight line then. So let's go down here. All right. Oh, okay. They really did not scale their sine values all that well. All right, so 1 goes along with about 8. I scrolled down a little bit too little. There we go. That's around what our graph is supposed to look like. So 1.02 goes with 8. That's about right here. Whoops. All right, right there. 1.41 goes with 12. So here's like 1.4, 12. 1.7 goes along with 13. This is this linear? This does not look linear. Am I plotting something incorrectly? No, everything seems okay so far. Weird. There's no way this is linear, actually. Hold on. F of t over... No, this should be linear. Why is this not working? Okay. Uh, 1.02 goes with 8. Yes. 1.41 goes with 12. 1.7, unless I did my sine values wrong, but I don't think I did. Yeah, okay, let's just keep plotting and let's see what happens. Um, all right. 1.94 goes along with 17, which is right here. And then this is a terrible data set, actually. Yeah. Uh, that goes right up here for the last point. Okay, yeah, that is pretty bad. But I know I'm pretty confident that I calculated my stuff correctly. So yeah, let's just go ahead and draw our best fit line. That last data point's kind of, or that fourth data point's kind of concerning me a little bit, but I don't see much else aside from the fact that I maybe put it a little bit too far to the left. Um, so I don't think that's really going to change my best fit line all that much. So I would maybe put it like right here instead. Yeah, but again, that's such a weird data set. Okay. That just kind of goes to show you that you can't just plot 3 data points and assume it's linear or square root or something. It's hard to tell. All right, these are the 2 data points I'm going to use to compute my slope. So 0.5 and 4, and then 1 and 8. So my slope, because I know I'm going to have to do that eventually, is going to be 8 minus 4 over 1 minus 0.5, which is 4 over 0.5, which is 8. And we're going to have to calculate the experimental value for the mass. So I got a slope of 8. What that represents is if I take f of t divided by 1 over sine theta, that should give me my slope, which we said is equal to 8, and that should be everything left over. So 5 mg over 6. G is 10, so 8 is equal to 50 m over 6. That's 25, 3, and 4. So 12 over 25 is my mass, which is 0.48 kilograms. There you go. So about 0.5 kilograms, give or take a little bit. They will give you a range of leeway for that too. All right. Okay. Hook, line, and sinker. We're on the last question here. So, in scenario one, a dude holds a block, with, fresh water, and the block is released and accelerates upward. So it has, and then you have salt water with a higher density. And you have to determine which one's going to be a greater acceleration. Well, the block has lower density, which means it's going to have a lower um that means that the bigger the difference in density, the bigger the acceleration. So A1 is going to be less than A2 because of that. Justify in terms of all of the forces. The block has the same gravitational force in both cases, but a bigger buoyant force due to bigger fluid density or greater fluid density and greater buoyant force, whatever. Um, Greater fluid density. So the net force and therefore, and I'll move this up in just a second, the acceleration of the block is larger with salt water in the second case. There you go. Okay. Move that up a little bit so you guys can see that. Hopefully. No? Okay. All right. Well, let me just go ahead and scroll then. There you go. Yeah. So that's my reasoning. Same gravitational force, bigger buoyant force, which means bigger net force and therefore bigger acceleration. So A1 is less than A2. Consider a general case and derive an expression for the initial upward acceleration. Well, sum of all forces is equal to mass times acceleration. That's buoyant force minus gravitational force is equal to density times volume of the block. Hold on. No, we can leave mass in our answer. So M A, right, buoyant force is equal to rho VG because the entire block is submerged. It'll just be the volume of the block minus the gravitational force, which is mg, and that should equal ma. Therefore, really, this is easy. Rho v minus m all over m times g. That's your acceleration. Wow, okay. They should have given you the density of the block, I feel like, to make it a little bit different and just kind of show you that's the difference in densities that affects acceleration. Okay, indicate whether the expression is or is not consistent. It is consistent because acceleration is directly proportional to density. Everything else is constant, therefore bigger acceleration. I'm not even going to write that down. All right. Yeah, that's it. That's the end of the exam. Thank you guys so much for watching. Have a great summer. Yeah, and hopefully hopefully this video was helpful. There we go. All right. Yeah, take care, guys.